We're talking about AC circuits. In an AC circuit, the power supplied to the circuit is changing sinusoidally, as is the current through the circuit. The power delivered to the circuit is also changing as a sine wave. We need an easier way to talk about these values. Let's talk about RMS values and power in AC circuits. If we do a quick comparison between a DC circuit and an AC circuit, we see that in the DC circuit, the current is always at its maximum value. And in an AC circuit, the current spends most of its time less than its maximum value. Because we have this situation where it's always changing, we want to come up with a term, sort of like an average value that we can use when we're talking about current in a circuit, or voltage applied to a circuit, or power dissipated in an AC circuit. But you can see we run into a problem. We have a sine wave. What's the average of a sine wave? It's zero. Half the time the sine wave is positive, half the time it's negative. We average it, we get zero. That doesn't help us very much. So we pick a special way to do an average. We call it a root mean square value. What we do is we square the value first. So if this is current versus time, we square the current. That ensures that everything is positive. Then we average it. Then we take the square root. This is called the root mean square value. So for the current, the RMS value is equal to the instantaneous value squared, averaged, and then we take the square root of that. We could do the same thing for the voltage. Now, for sine and cosine waves, we know what this value has to be. It's 1 over the square root of 2 times the maximum value. So that's true for the current. It's also true for the voltage. And we can use these values in our standard equations. If we want to know the power delivered to a device, we can use our old equation for a DC circuit. Gave us power is I squared R. And if we want to know the power delivered to a resistor in an AC circuit, we can say the average power is the RMS current squared times R. This also enables us to use tools like digital multimeters when dealing with AC circuits. A digital multimeter just reports a single number, right? A digital number in the display when you measure a voltage or a current. So if you're measuring a voltage that's changing, constantly changing in time, you'd have a hard time with that. The number would always be changing. But if you change your multimeter from DC to AC, it will report the RMS value. So you take it and you plug it into the wall. In the United States, what do we get out of our wall outlets for a voltage? 120 volts AC. What is that? That's the value you'd get if you plugged a multimeter in and measured the voltage. That's the RMS value. So what's the peak voltage going to be? Our peak voltage hits a maximum of about 170 volts. The RMS voltage is the maximum voltage divided by the square root of 2. And that's what you'd read with the multimeter. I want to talk a little bit about resonance in RC circuits. This is very similar to what we learned in mechanics about oscillating systems. First, let's look at just a simple case where we don't have any resistance in our circuit, an LC circuit. In this case, we already talked about the fact that the energy will oscillate back and forth between the electric field of the capacitor and the magnetic field of the inductor. That's just like our mass on a spring. If we ignore friction and air resistance, we pull that mass down and let go, and it oscillates back and forth, back and forth. The energy is being transferred from potential energy in the spring and gravitational potential energy to kinetic energy of the mass, back and forth. Because there's no resistance, the mechanical energy stays in the system. It doesn't dissipate out and turn into heat or other forms. It stays in the system, and our system will oscillate back and forth forever. Now, if we add a resistor to our LC circuit, we have an RLC circuit, and that resistor is going to dissipate a little bit of energy every time we go through a cycle. The capacitor charges up, the current stops momentarily, then it switches, the capacitor goes to zero charge, and we get all the current that hits its maximum value, and the energy is in the inductor, and then it goes back into the capacitor. But now the capacitor doesn't have quite as much charge on it as it did before, because the resistor dissipated a little bit of energy as heat. And every time you go through a cycle, the amplitude gets a little bit less, and eventually we have no more current, no more energy stored in this system. That's similar to the mass on the spring when we take into account friction and air resistance. I've exaggerated the effect by putting it in some fluid, but that fluid could be air, and every time the mass goes up and down, the amplitude gets a little bit smaller because we're losing some mechanical energy into heating up the fluid around the oscillator. And our last situation is a driven RLC circuit, where we're adding some energy with our source. Of course, the resistor is dissipating some of that energy, but we're adding energy, and we've got this oscillating system. Think about the analogy, the mass on the spring. If we add energy at just the right frequency, the amplitude builds up. It gets bigger and bigger and bigger, kind of like pushing somebody on a swing set at the park. If you push at just the right interval, the person in the swing starts to swing in a bigger and bigger amplitude. If you push at the wrong interval, then their motion is kind of haphazard. Nothing really happens. Sometimes you're adding energy, sometimes you're taking it away. But if you push at just the right interval at the natural resonant frequency of the oscillator, then all the pushes add up and the amplitude gets bigger and bigger. And the same thing happens in an RLC circuit. Now, this oscillating effect doesn't have anything to do with the resistor. It has to do with the capacitor and the inductor and how they hand off the energy back and forth between the two of them. So we would expect our frequency of the circuit, the natural frequency of the circuit, to depend on the capacitance and the inductance. And our angular frequency of oscillation for a circuit with a resistor and a capacitor in series is 1 over the square root of LC. So the current in the circuit responds as we change the frequency that we're delivering power to the circuit. And at certain frequencies, at the resonant frequency of the circuit, it hits its maximum value. We end up with a graph that looks something like this for the current in the circuit as a function of the frequency that we're driving the signal with. So we start increasing the frequency and we don't get much current in the circuit, and all of a sudden we hit this magic value, the resonant frequency of the circuit, and it responds and we get a big current through the circuit. And as we continue to change the frequency, it drops back down again and we get a smaller current. You can see that the resistor does have some effect on the shape. The smaller the resistance, the more defined this peak is. It's higher and narrower. You might be wondering what the applications are. There are a couple of interesting ones. One is a metal detector. You might have seen somebody at the beach walking around. At the end of that metal detector, there's a coil of wire. That's an inductor. And they scan that back and forth over the sand. It's being driven at the resonant frequency, so the circuit sees a big current flow. When that coil of wire goes over a piece of metal, it changes the inductance. It's like putting an iron core into a coil of wire. You greatly change the way that coil of wire responds to current. You change the inductance. When you change the inductance, the resonant frequency changes and the circuit doesn't respond. The current in the circuit drops way down because you're not at the resonant frequency anymore, and that can be detected. Another example is tuning an old radio to a radio station. The antenna on your car is being hit with every frequency from every radio station. And if you live in a big city, there are lots of radio stations, almost no empty spots. They're all taken. How does your radio know which one to play? Well, you have an LC circuit. You're dialing in. That dial is connected to a capacitor that can change capacitance. And as you change the capacitance, you're changing the resonant frequency of the circuit. And whichever frequency is at the resonant frequency of the circuit, that's the one that creates a big signal in the circuit and can get amplified and sent to your speakers. That's the radio station you listen to. And you change the resonant frequency a little bit, and that station drops out, and the next one is the one that excites the circuit and causes the radio to play that station.